Okay, I see one question from Dima.
I actually have a question for Biao. So thank you for a great talk. So
Yeah.
my understanding was that you considered a system without any disorder in it. So is it possible to comment what would happen if you have disorder? Because if you want to connect this with quantum Hall effect, that would be inescapable.
Right. Yeah. Yeah, that's a very good question, actually. So, yeah. So, indeed, for instance, from some scaling dimension analysis, if you have disorders, um, for instance, the scaling dimension of the four-formula interaction becomes irrelevant. So probably for that problem, um, yeah, it's actually hard to study exactly what happens, but you would expect yeah, maybe the chaotic behavior is weaker or something, but still, I don't think the disorder actually would recover quantum coherence. So on the other hand, uh, yeah, basically, how strong the chaos is not quite well characterized. So disorder basically, as we understand it, it's just a yeah, it's kind of some single particle potential for fermions, for example. It shouldn't further destroy your quantum coherence or recover. So in that sense, I would expect, although the fermion interaction becomes irrelevant, I would expect you still have quantum chaos. But on the other hand, if you have disorders, yeah, basically all the scaling dimension of the other analysis could change. Yeah, it's just very hard to analyze analytically or numerically at this stage. Yeah, also, yeah, yeah, basically, yeah, that's what I know so far. But for example, for the Anchor 4 case, basically the most well-known Carl-Lattinger liquid, if you have disorders, the interaction is actually, for instance, yeah, basically what disorder does is it kind of rotates your Majorana basis as a function of X. And in that case, in this special case, the interaction is actually it's actually a singlet under the SON rotation, the SO4 rotation. So in this case, you don't expect any effect of the disorder. It should still remain coherent. While in the large N limits, actually, you again have some effective SON symmetry. So again, disorder seems not that important in this sense, and you would expect the chaos to persist. That's my expectation.
If you go to the regime with full SON symmetry, then unless you have n exactly equal to 4, all these 4 fermion couplings must be also random. So and
Right, yeah.
Right?
Right. So this does not apply to 5 or 6 or other small n's. But I mentioned this as ON rotation symmetry is because we noticed that the Green's function, the 2-point function of n to the 4, is actually equivalent, yeah, equal to take the same form as n to infinity. So I haven't understood that very well, but one thought I had is the 2-point both have SON symmetry that might put some constraint on the Green's function.
So I wonder how important it is for you that the scaling dimensions were nice rational numbers, so a set of well-quantized numbers. So in practice, that's what we write when we have a bunch of modes running in the same direction. But actually, say gallium arsenide is a piezoelectric material. When you look at the phonon coupling with the edge, you discover that it very slightly shifts all critical exponents. We always neglect that effect, but it exists. So they are never actually exactly quantized. Does it make sense for? Does it make any difference for your quantum house story, or you can say that nothing is exactly marginal? Things are either slightly relevant or slightly irrelevant.
I see. Yeah, that's interesting. So we are actually constraining only in the pure one-dimensional case. Then that's exactly marginal. But you're mentioning if considering the bulk degree of freedom, that's actually have some effect. Yeah, that's probably making the things more
Numerically,
chaotic. Yeah.
it's very
Yeah. So, but I think I would expect this effect. So basically, you see, yeah, the additional phonon contribution, the electron phonon interaction itself is I think is irrelevant. Although yeah, it could contribute to flows. So
no, it's a piezoelectric. It's a piezoelectric material. So three-dimensional phonons are capable of shifting critical exponents a little bit because it's piezoelectric. Okay. So it's a special thing about arsenide. And of course, we need three-dimensional phonons because it is actually three-dimensional.
I see. Yeah, that's interesting. Yeah, actually, one thing I want to mention.
Numerically, that's extremely weak effects. I'm just asking an academic question, really.
Right. Yeah. Numerically, it would be hard. Yeah, one thing I want to mention is if you look at non-chiral examples, there are actually studies of the 1D non-chiral SYK before ours. In that case, they showed in the large N limit, the interaction is marginally irrelevant. So that's kind of a less interesting example. If you have non-chiral interactions, in some sense, the chiral interactions give you more interesting things.
Yeah. Thank you.
Yeah, thank you for the question.
I see a question from Simon Kleptov.
Hello?
Yeah.
Can you hear me?
Yeah, we can hear you.
A question for Hugo.
Yes.
So maybe it's a very naive question. You work on the plateau where Hall conductance is 1/3, right?
Yeah. So
is it possible at all to measure what happens with the signatures of fractional statistics when you start to slightly deviate from 1/3?
Yes.
Does the question make any sense? I don't know.
Yeah, you mean so we are performing the measurement on the middle of the plateau.
Yeah.
We could make measurement around here, for instance, to
right.
see how we deviate from this perfect 1/3. Yeah, that's a good idea, but we didn't have time yet to do this measurement. But good idea.
Do you expect this fractional statistic to disappear when it deviates from the exact from the middle of plateau? Or
I would say I'm maybe not the best person to ask this here, but I think yes, we should. If we deviate, we start to have some back reflection. I would say that it will vanish the fractional signature, but just maybe someone has a more precise.
But there are no kind of predictions to compare how it would like what would happen when you start to deviate. Maybe theoretical predictions.
Okay, I don't know much about this prediction.
Okay. All right. Thanks a lot.
I could comment on that. So,
yeah,
so I think when you mean, of course, when it's at low temperatures and still on the plateau, but off to the sides of it, they're just localized states, and presumably they don't affect things at low enough energies, but at high energies it would. Once you start getting into further off the plateau where you start getting bulk, if they're now basically free carriers that are very non-localized in the bulk, I think you're going to get pretty non-universal corrections, would be my guess. But of course, it depends on how much there is.
So this will be like kind of, because we have done some variation of this factor with temperature, and we see that signature disappeared with temperature. Above 50 millikelvin, it starts to vanish. So it might be a part of the answer.
Okay, thank you.
Any more questions? So let me take my chance to ask Biao a question.
Yeah.
In your calculation, is this the SUN symmetry is very important, or you can, like, I think that my question is similar with the Professor Habrin question. When you make the different velocity between the mode, is this like very hard to do the calculation, or you still can do the calculation?
Yeah. Actually, I can make more comments about that. That's a very interesting question. So yeah, I earlier mentioned if you have velocity anisotropy in the fermion model, in the Majorana model we studied, yeah, at least from level statistics aspect, it starts to show Wigner Dyson. If you, basically it's a probably there's still computation between the velocity anisotropy and the interaction strength. When these two are comparable for n smaller than smaller than 7, your system also become chaotic. You see some Wigner Dyson distribution. But yeah, I guess level statistics is not clearly identical to quantum coherence studies, etc. That's still under study. Whether how strong that effect would be if you try to do some interference detections. That's one question. So the other is it's not always the case that when you add velocity anisotropy, you lose the integrability. For instance, in the Samian model I presented, the anionic examples, the bilayer Fabian, even if you include the Majorana fermions in the Fabian state and add velocity anisotropy, it seems still integral. Basically, the interaction you can write down can still convert into some free fermion picture. There are also similar examples. So there's kind of many interesting examples. Different. Yeah.
And in your model, you seriously need the chirality, right? All the mode move in the same direction.
Yeah, so far we focused on the chiral model, but yeah, basically mostly because the chirality actually preserves the scaling dimension. That makes your analysis easier. You could make use of the so far we are also been only considering scaling invariant interactions that you can make use of the scaling invariance to give you some to simplify your calculations. But it's certainly very interesting. Even for chiral systems, you could have relevant interactions, and it supposedly it's not gapping the edge; it's doing something differently. And also for non-chiral edges, there are also just ungappable non-chiral theories. Yeah, that's an interesting question we haven't explored yet.
Yeah, I asked this question. I asked this stupid question because of the following reasons. Because I'm thinking, like, if you have two quantum holes with two S and go close to each other, and you allow the tunneling between them, then I think that you can have a lot of S mode to make your n equal to 7.
Yeah.
And in this case, maybe you can see the chaos in the real experiment.
Yeah, so I think the 7 roughly accounts for 3.5 complex fermions. It's not a super high. Yeah, so I guess one thing is how strong would the interaction be actually, and also it depends on how large the interaction strength compared to velocity and anisotropy. So it's a little bit complicated in this example, but there are simpler setups actually. So one thing we've been also studying still in progress is for 4/3, you could basically tune the system to have either chaotic or integrable cases.
Interesting.
That's a maybe more testable example.
See, so you can tune the sharing of the interaction to have the.
No, basically you can tune the symmetry of the system. For instance, you add superconductivity to it. Yeah.
I see. Okay, thanks. Very interesting.
Yeah.
Okay, so if there's no more extra question, we can go to the open discussion on Discourse. Thanks everyone, and thanks the speaker today. A lot of interesting talk.